Think you need fancy tools or a big budget to build a smart robot? Think again. In this video, I'm turning a cardboard box, some basic parts, and a Raspberry Pi into a working robot that drives, follows lines, avoids obstacles, and even dances, all without soldering or 3D printing. If you're a beginner, this project is perfect for you. Let's get building. Hey everyone, I'm going to walk you through how to build your first Raspberry Pi powered robot using the CamJam EduKit 3. This kit is affordable, fun, and perfect for beginners. In this step-by-step guide, will unbox and wire every part from motors to sensors, set up the Pi, grab code from GitHub, and if you've already not flashed your operating system, I recommend watching this video. We'll also cover how to bring the robot to life with 5 awesome milestones: driving, line detection, speed control with pulse width modulation, distance sensing, obstacle avoidance, and a bonus dance routine. I'll show you all the wiring diagrams, explain each Python script in simple terms, and even show you how to make your robot run these programs automatically every time it turns on. By the end, you'll have your own fully working robot and a strong grip without needing any advanced tools. Let's delve into the CamJam EduKit 3, a beginner-friendly robotics kit designed for Raspberry Pi enthusiasts. So what's inside the box? The box comes with 2 DC motors with 2 red wheels, a ball caster that serves as the third wheel, a line-following sensor, an ultrasonic distance sensor, resistors, a small breadboard, some jumper cables, a custom-designed motor controller board with screw terminals, 2 pieces of strong 3M padded double-sided tape, a battery box for AA batteries. Batteries are not included. A sturdy card box which can be repurposed as the robot's chassis. Additional components required to complete the build are a Raspberry Pi Zero 2W, a micro SD card with the Raspberry Pi operating system installed, a monitor and appropriate HDMI cables, a keyboard and a mouse, a portable power supply such as a phone power bank. If you're new to setting up the Raspberry Pi Zero, consider watching the linked video tutorial for a step-by-step guide. Once you have everything ready, you'll need to prepare your cardboard chassis. To make the necessary holes, I simply use a sharp wooden skewer from my kitchen. It's quick, effective, and readily available. Just be cautious while handling it. To simplify the setup process, clone the official EduKit 3 repo directly onto your Raspberry Pi. So from your Pi terminal, after updating it using the sudo commands as shown on screen, run git clone and the GitHub link that CamJam EduKit provided, which I've also included on my screen. This command downloads all the necessary project files and worksheets, providing a structured path to building and programming your robot. Begin by cutting the 3M double-sided tape in half. Use one half to firmly attach each motor towards the bottom end of your cardboard chassis. Next, attach the caster ball to the opposite end of the chassis using another piece of tape. Now, carefully pierce 2 small holes in the chassis using a sharp kitchen skewer or similar tool. These holes will allow the motor wires to pass neatly to the top. Once that's done, press the wheels securely onto the motors. Next, insert the AA batteries into the battery box. Use your remaining tape to attach the Raspberry Pi Zero on top of the battery box to make sure that it's stable. Let's now connect the battery box wires to the motor controller board. Make sure the black wire is attached to the terminal marked ground and the red wire connects to voltage VCC. Double check these connections. Incorrect wiring can damage your controller. The motor controller board provided is an H bridge, a circuit that allows your Pi to control the direction of your motors, making your robot move forward or backwards. Let's now connect the motors. Attach the right hand motor wires to the terminals labeled motor A and the left hand motor wires to motor B. Refer to the provided diagram for additional clarity. Use a screwdriver to carefully tighten all terminal screws. Loose wires can cause unreliable connections. Now gently place the motor controller board on top of the Pi as demonstrated. Insert your SD card into the Pi, then connect your power bank to power it up. If everything is correctly connected, you'll see the activity LED flicker on your Pi. Let's now test our motors. So this script, which we've got by cloning the repo that EduKit provided, configures 4 GPIO pins to control the forward direction of the two motors. It ensures they're all off at the start, then briefly powers each wheel forward for 1 second. Finally, it cleans up the GPIO settings before exiting. This testing code is found inside the rpio.gpio folder, the repo you've cloned earlier. So if you navigate to the code folder, you'll see a script specifically for motor testing. To make your robot automatically run this code upon reboot, you can use cron. Just specify the script location in your cron setup and your robot will automatically run the motor test every time it powers up. Now your robot should be ready for action. Alright, let's get our robot moving. First, make sure you've cloned the EduKit code from your Pi. Mine lives under my home directory under my username followed by EduKit3, rpio.gpio0, and then code. To launch the driving demo on every boot, edit your cron tab with @reboot cd, specify the folder structure for the path. After, use the end symbol followed by /user/bin/python3 and specify the code that they've provided, which is for driving2.py. That way, as soon as the Pi powers up, it will run our driving script automatically. So for this code, we begin by importing the GPIO and time libraries, setting up the BCM mode, silencing warnings, and configuring pins 10 and 9, which are responsible for the left wheel, and 8 and 7 for the right wheel as outputs. And we have 4 helper functions: the stop motors, the forward, the backwards, left, and right. They let us cut power, drive straight, reverse, or pivot in either direction. Going over the demo, as you can see, we run forward for 1 second, pivot left, for half a second, forward again, pivot right, then briefly reverse before calling stop motors and GPIO cleanup to reset the pins. Now let's add the IR line follower to our robot. This little 3-pin module marked VCC, ground, and out uses infrared light to tell black from white. I ran out of the 3M double-sided tape, so I'm basically using a product called Woohoo Tack, which is a removable adhesive putty to attach the IR sensor. We also need to poke a tiny hole in the chassis with a skewer so the wires stay neat. When it comes to the wiring, it's pretty straightforward. The ground can be attached to the ground rail on the EduKit controller board, the VCC to the 3V3, which is basically the sensor that runs the 3.3 volts, and the out should be connected to GPIO25 of the motor driver. Use 3 female to male jumpers for sensor pins to connect back to the controller board. In the loop, we read 25, which is a 0. Low means the sensor sees black, and 1 for high, which means the sensor is seeing white, printing the results every 0.2 seconds. Slide the robot over, alternating between black and white areas, and watch the console instantly report black line detected or white surface detected. If the readings are inconsistent, tweak the sensor's height above the surface until it reliably picks up the contrast. Hit Ctrl+C to reset the pins when you're done. Before we dive into the 2 pulse width modulation scripts, remember that controlling and calibrating your robot's speed is key to smooth turns and consistent behavior. We use pulse width modulation to switch each motor pin on and off at a fixed frequency and vary the duty cycle, which is how long it stays on each cycle. Example, 30%, to set the motor speed precisely. Now let's run the first demo. Play the first script and watch the robot move forward, pivot left, forward again, pivot right, then reverse, using the same duty cycle on both wheels. You'll notice any drift as one wheel overpowers the other if you were to place it on the ground. For this demonstration, I'm just doing it on the air. Next, let's now run the second demo. So for this script, this time they've split the duty cycles into duty cycle A and duty cycle B, letting us fine-tune each wheel speed to eliminate drift. When you run the first script, expect a controlled but potentially veering forward, left, forward, right, reverse routine. With the second one, which is this one, it shows how tiny adjustments to each wheel's duty cycle instantly corrects that drift, resulting in cleaner, more precise turns if you were to run this using cron on the ground. Next, we'll add an ultrasonic sensor so our robot can see distances in the real world. Start by bending two resistors into the breadboard. As shown in the diagram, the 330 ohm resistor, which is orange, brown, this goes from the sensor's echo pin to a spare column, and the 470 ohm resistor, which is yellow, purple, brown, goes from that column down to the ground rail, which you can also see as I'm demonstrating it here. This resistor divider safely drops the echo signal from 5 volts to Pi friendly 3 volts. Wiring is straightforward. You would have to connect the ground rail. Initially, we've used the ground rail for the IR sensor, so this time we can share the IR sensor's ground by unplugging it and replugging both grounds together on the same rail using the breadboard. The VCC would connect to the 5 volts on the motor driver board from the ultrasonic sensor, connect trig to GPIO 17 and echo to GPIO 18 through the resistor. I'm going to be sticking the breadboard in place with removable tape so everything stays put on my chassis. Feel free to experiment how you'd like to place your ultrasonic sensor. So going over the code that they've provided for measuring distance on a high level, we start by configuring pin 17 as output, which is for trigger, pin 18 as input, which is for echo. In a loop, pull trigger low for 0.5 seconds and sense a 10 microsecond high pulse, then wait for echo to go high and back low, timing how long the echo takes to return. When it comes to computing the distance, the elapsed time is multiplied 34,326 centimeter per second and divided by 2, and then this gets printed, pauses half a second and repeats. As you can see from this live demo, when we run the code, you'll see this live distance readings printed every 0.5 seconds. Place an object or wave your hand in front of the sensor. Confirm that it's working before we move on to our next module. Alright, time to make our robot follow a black line. First, make sure you've gone the EduKit repo into your Pi. Mine lives in my home user directory, followed by edu3, RPIO, GPIO, followed by code. And make sure you add this to your cron app so it runs on every boot. So at reboot, cd followed by the path you've specified the code to be saved at, and then a dash followed by user a dash bin Python 3 and the code name, which is linefollower.py. Going over the code, we basically import the GPIO and time. We switch to BCM mode. We have 4 functions which are controlling our movement forward, backward, left, right, and then last one for stopping the motors. We have line detection set pin 25 being set as an input, is over black returns true when the sensor reads low, and false for white. If the robot drifts off the line, is over black becomes false. Seek line kicks in. It alternates small left or right pivots, each slightly longer than the last, until the line is found or a maximum search count is exceeded. And our main loop continuously checks the is over black function is true or false. If it's true, it calls the forward function, keeps the boat on track. If it's false, then calls seek line. If the line is found, it resumes forward and prints following the line if you had it connected remotely. In my case, I am not remotely connecting, I'm just having it run on cron, so I'm not able to see following the line being printed. And if not, basically halts completely and prints the robot has lost the line. Let's now have the robot in action. As you can see, the robot will drive forward along the black tape. It breaks the moment it loses contact, scans left and right until it reacquires the line, then smoothly continues. It's a perfect beginner project for autonomous path tracking. Alright, let's now get to the fun part. Let's get our robot dodging obstacles. First, make sure you've loaded the EduKit code into your Pi. Mine lives under my home directory followed by my user, EduKit3, RPIO, GPIO followed by code. To launch the obstacle avoidance demo on every reboot, add this to your cron tab, which is at reboot cd, specify the path that you have the code saved at, and then have end followed by user, followed by bin, followed by Python 3, and name of the code, which is obstacle avoidance.py. So for the code that they've provided, they are basically importing RPIO libraries, time libraries. We're switching to BCM mode. We're silencing, warnings, configuring pins 10 and 9 for the left motor, 8 and 7 for the right, plus pin 17 for triggering, pin 18 for echo. We create the pulse width modulation channels at 20 Hz for each motors and define movement functions such as forward, backwards, left, right, and also stop motors. We have distance measurement and the function measure, which fires a 10 microsecond pulse on trigger, then time how long echo stays high, converts that to round trip time into centimeters using the speed of sound, handling 2 plausible those cases if the echo never drops. When it comes to the obstacle logic, we have the main loop which drives at 30% speed, pausing every 0.1 seconds. All is near obstacles function which prints the current distance and returns true if it's under 15 centimeters. On detection, it stops the motor's reverse for 0.5 seconds, pivots right for 0.75 seconds through the avoid obstacle function, then resumes forward motion. Now that you have an understanding of the code, let's run the demo and watch. As you can see, the bot cruises until it spots something in its path, reverses, swings right, go round, and then drives on, all without a single bump. As a bonus, I wrote an advanced motor.py script to show you how to build higher level motion routines, everything from simple forward back to a full dance sequence to launch it on every boot. So add this to your cron tab, create a new file for saving the new code, which I've also included in the description. Call it advanced motor.py and paste it here. And once you have that, we would want it to run on reboot. So specify the paths using @reboot cd, specify the paths at which you save that new code, and then have that user bin python 3 structure, and then write the script name, which is advanced motor.py. So going over this code, we used BCM pin numbering. We have all the same structure as last time. And then we have our core helpers, stop, which kills all motor signals and waits a moment, forward duration and backward duration. They drive both wheels for a given time, then call stop. We have turn right duration, which is responsible for left wheel forward and right wheel reverse, and then turn left duration, which do in place pivots. And then we have zigzag function, which alternates short left and right pivots while moving forward for a shuffle. And the dance sequence does a warm up by start going for 1 second forward, 1 second back, spins out for 0.7 seconds, turns right then left, and then does a zigzag shuffle, 4 repeats of 0.3 second pivots, followed by a square dance, 4 cycles of forward plus 90-degree turns, and a final wiggle, 3 quick forward back bursts. Run the script and watch your robot breeze through each step from a smooth drive to a full dance routine, demonstrating how modular helpers can unlock complex behavior with just a few lines of code. When going over this project, I came across some issues and was able to resolve them. If you're having some issues, something is not working, these are some troubleshooting tips. So if your motors don't spin at all, the likely cause could be that you're using the wrong GPIO numbers in code, or you might have loose motor drives. So double check your constances. There might be some troubleshooting tips that you might encounter following this setup. So if you run into any of them, I've included a link that would give you access to a troubleshooting tip to help you get unstuck. Keep this sheet handy. And just like that, we've turned a cardboard box and some simple parts into a fully working robot. It drives, follows lines, avoids walls, and dances. You've learned how to connect motors, read sensors, and write smart Python code that brings your robot to life. If this project helped you, smash that like button, subscribe for more hands-on Pi builds, and let me know in the comment what upgrade you want next. Drop your ideas below, and I might feature the best viewer builds in a future episode. Until then, keep building, and remember, every great robot starts with a single line of code.